Acid-catalyzed dehydration. Dehydration means taking away water. Water is getting gone. So alcohol can be converted by dehydration. So what does that mean? It means we're going to get an elimination of water from carbons next to it. Primary alcohols must be heated at very high temperatures to do this. And it's got to be in the presence of an acid catalyst. Good examples are sulfuric and phosphoric because they're very strong with their first deprotonization. Secondary alcohols can do this at lower temperatures. They're much easily manipulated. And tertiary alcohols, they can do it pretty much at any, basically a little bit warmer than room temperature. Like think about if it was a hot day and you had your air conditioning on, but you're at grandma's house, so grandma keeps it pretty hot in there and you're like, oh, it's really hot. It's not like you're boiling. It's not like you got a stove on. It's just warmer than you'd normally like it to be for room temperature. So how does this work? Well, when we talk about ease of acid-catalyzed dehydration, we're talking about how easy is it for this water molecule to come off. Well, primaries are worse than secondaries, which are worse than tertiaries. That's why the primary alcohols have to go in with such high heat and with a good acid like sulfuric or phosphoric. Secondary, just some high heat, don't need anything else in there. Tertiary, it can do it with anything. So if we look at this primary, my pen is not working very well today, guys, sorry. This secondary and this tertiary, I need to get a new stylus, y'all. Okay, so that's your tertiary. What's happening? We got very high heat with the acid. We got just the acid and a significantly lower heat. And then we got really low heat and an acid with that one, okay? And what do you see happening? We see a double bond being formed here. Right. I'll get my next stylus for the next video, guys. I'm sorry. We got a double bond formed there and a water coming off. Why? Well, because we're getting this coming off and one of these hydrogens. All right. Same thing is happening for the secondary. One of those is coming off. And what would be a hydrogen here that we don't write because it's understood, that goes away also. Double bond is being formed. Water is coming off. Our tertiary, one of those is coming off. And one of these hydrogens is coming off. That's where our water is formed. And again, a double bond is reformed. Don't worry too much about this. All right, so when we talk about dehydration of a primary and secondary alcohol, we are going to get rearrangement. That's why we get a racemic mixture, because when we get the rearrangement and our double bond is formed, it's happening because we have a rearrangement. If you look closely here, it's going to be a, let's see, 1, 2, yep, we're going to get a methyl shift here. That's what this is, okay? And we can form the double bond here, or we could have formed it here. It's going to be much more stable to have that double bond between those two tertiary carbons than it is to have it between a primary and secondary carbon. So that's why we see the major product as being the 2,3-dimethyl, diethyl 2-butene. Because it's much more stable to have that double bond in the middle than for it to occur between a primary and secondary carbon. So how are we doing this? Well, here we have a secondary alcohol. Okay, that's our secondary alcohol. It's going to grab onto that hydrogen from the hydronium ion. It's going to form this oxonium ion. Remember, that should be in your brain at all times. Pretty much the very first step of any of these removals is oxonium ion. Next is to break the bond. So we get our carbocation intermediate. So that's going to break here. And we get our secondary carbocation. This is our slow rate determining step. And water as a product. Well, what happens next? We got to take a proton away. Why do we got to take a proton away? Because we got to reform that double bond. So the oxygen is going to come grab the hydrogen, and these shared electrons are what is going to form that double bond. We can get both cis and trans. So here's our trans. Here's our cis. So we can get a racemic mixture here. When we talk about the carbocation intermediate followed by migration of an atom or a group, remember migration just means shift. That will happen if I form a secondary carbocation, but that carbocation is next to a tertiary. We know that to be true. This comes off, leaving our secondary carbocation intermediate, and therefore we get the methyl shift. When we get this methyl shift, we now have a tertiary carbocation intermediate, which is significantly more stable. Now, how would we have gotten this one down here? Just depends on where the hydrogens break their bond. Now, primary alcohols with very little beta branching will get a terminal alkene and rearranged alkene. So this also will be a racemic mixture. The majority is going to be the trans and the double bond occurring between two secondary carbons. Okay, the trans is more stable than the cis because of strain. All right, so that's why trans is the major product here. Cis, close second, and then of course the primary alkene, not very much at all. But we do get this racemic mixture, and we're going to get it by way of E1 and E2 reaction mechanisms. So you can go through this and see how all of this occurs. It's just how are we getting the different the different products, whether it's a primary alkene or a secondary alkene. Note how E1 and E2 play a part in this. Remember, E1 is when a carbocation intermediate is formed. E2 is when things are coming on and kicking off simultaneously. This is where you're going to get your shift. In this case, it's a hydride shift. Why? Because it's a secondary carbocation or a secondary carbon. There is no tertiary, so there cannot be a methyl shift. There is no methyl to shift. There is only a hydrogen to shift. Therefore, we get the hydride shift. Once we form that new carbocation, that's where we get this cis and trans to alkene. I would like you to go through this pinnacle rearrangement. It's important in that you understand how the rearrangement occurs and why. I'm not going to require you to do a reaction mechanism with this, but you need to understand what the final product is. All right, so again, note, oxonium ion formed, shocker. We've said that about 18 times so far this lecture. Second step, break a bond to give the stable molecules. So our carbocation is formed, and it's a tertiary carbocation. If it is a tertiary carbocation, will there be a shift, either hydride or methyl? Chances are no. Could one occur to get a racemic mixture? Maybe. But a tertiary carbocation, very stable. Don't need it. But if there's a shift, Then we'll get this cut off, and these double bonds. I'm sorry, I just did this backwards. I'm sorry. No, eraser. Okay, if we get a shift, then these lone pair of electrons will go back to form that double bond. Okay, so we get this stabilization of the carbocation by delocalization. What does that mean? That means there's a constant switch between the lone pair of electrons from the oxygen forming a double bond, and that double bond going back to the oxygen to form lone pairs. Last thing we do, take away this hydrogen. All right, we're going to form the hydronium ion, and we'll be left with this double bonded oxygen and the methyl group here. With the oxidation of alcohols, again, primary alcohols will get an aldehyde or a carboxylic acid. We've already talked about this. I'm going a little bit fast through this because, a lot of this we've seen earlier in the semester. Whether or not we get an aldehyde or the carboxylic depends on the conditions. What is in solution with the primary alcohol? We talked about secondary alcohols being oxidized to ketones, and tertiary alcohols are not oxidized at all. Why? Because they're perfectly stable and they don't need to be. So we're only talking about oxidation of primary and secondary alcohols. The primary will become an aldehyde or a carboxylic, depending, and the secondaries will go to ketones. We can do this most popularly with chromic acid. When we get the chromic acid, you'll see we'll get this or this. Okay, this is our aldehyde, and this is our carboxylic. All right. Jones reagent, which is just your chromic acid in the sulfuric acid, most common that we use for this. Secondary alcohols also use the chromic acid most popular, and that's how we're going to get our ketone. Note, this stays. We got a wedge here. It's going to become in plane. All right. And then tertiary, it's not going to be oxidized. Why? Because it's stable and it's good. You can't add another carbon-oxygen bond. You can't double bond because it's already, bonded to 3 different carbons. It's totally stable. It's not going to do anything. Tertiaries, no oxidation. Go through this reaction mechanism and look at it and see what's happening. Again, you need to understand it. I'm not going to directly ask you to write a reaction mechanism or to identify a reaction mechanism, but you do need to recognize it and understand it. That's it for acid-catalyzed reactions with alcohols. Your next lecture for Chapter 10 will be put up shortly.